So I'm very happy to introduce our speaker today, who's from our math department, but very especially he's actually also our alumnus. Professor I-Kun Chen was a graduate in 1999, but he was double major already between physics and he ended physics but double majored in math. But then he changed. He left us and went to and got a master's degree in mathematics department and spent 2 years as an assistant at Academia Sinica Mathematics Institute, and then went to Maryland and received his PhD in 2009. Afterwards, he spent 3 years at Academia Sinica as a postdoc, and subsequently spent a year at Jiao Tong University Applied Math Department as assistant professor, and recently just joined NTU Math. But if you look at the title, he cannot shake his physics background. Okay, so let's welcome Professor I-Kun Chen from Math Department, and his title is Boundary Singularity of Moments for the Linearized Boltzmann Equation. Okay.
Thank you for introduction and thank you for invitation. And as Professor Ho said, I was graduate from this department, so it's very nice to come back. And today my talk is about, my title is Boundary Singularity of Moments for the Linearized Boltzmann Equation. So basically, after my graduation and my research interests are majorly on the boundary phenomena for Boltzmann equation. And so maybe I should make a very little, this is my plan of talk. So first I will give us introduction, then I'll explain the boundary singularity for a special case. This special case called thermal transpiration problem. Thermal transpiration problem itself is interesting. And then finally, I'll show a general theory for the singularity of moments. And as we know, there are many different models for gases. One of the very successful model is fluid dynamics. In fluid dynamics, we talk about the evolution of density, flow velocity, and temperature. This model is successful, but for the physics near boundary, it cannot explain things that well. And the other way to see gases, we can consider gases as molecules, and they constantly collision with each other. So one way is to use classical mechanics, but in fact this is not a realistic approach, because the size of the system is in the order of 10 to the 23. So it's impossible to solve this kind of thing. So there is a way to deal with this. We use a statistical mechanics point of view, and the result is the Boltzmann equation. So maybe I should, now I would like to introduce Boltzmann equation. In Boltzmann equation, we are discussing this is called velocity distribution function. It is the function of space x, time t, and microscopic velocity zeta. Here is Cassie, sorry, Cassie. And this is density of mass at position x, time t with density, with velocity Cassie. And if we multiply this function with delta x, delta Cassie, it is the mass inside this small volume in the phase space. So this is basically the density of mass. And the Boltzmann equation written down as this. This is you can see on the right hand side. If you consider this term as 0, then this equation is called free transport equation. That means if a particle with velocity z c, it will proceed with that velocity in a straight line. But on the right hand side, there is a term called collision kernel. It counts two things. One is originally there is a particle with velocity c, and it hits some other particle, so it leaves the velocity distribution. And then so this term is called loss term. And the other scenario is there may be two different velocity, c prime and c star prime, and they somehow hit together, somehow collides and then create one particle with the velocity c. So this is called gain term. So if you sum up all the gain term and loss term, then you get the contribution from the collision. So this is basically the Boltzmann equation. So
how do you, is continuity automatic or conservation of mass?
okay, so in fact, I should say here that this equation has you can derive conservation of mass, conservation of momentum, and conservation of energy from this equation. But that is because the collision kernel, if you has a property that if you hit that with the contribution of a collision kernel will. Okay, so basically, maybe I should say this. This we have this property. And the collision kernel has these three properties, and that means conservation. That will derive the conservation of mass, conservation of momentum, and conservation of energy.
So my question is that it's automatic from this form.
Okay, so the collision we consider we consider the elastic collision. So it conserves momentum and energy. And the cross section B is depending on the potential. So basically it conserves the momentum and the energy. Okay. And there is a property for the collision kernel. That is, this collision do not have any contribution if and only if the distribution is Gaussian. And this Gaussian is written down like this form with 5 parameters, with temperature, velocity, and flow velocity, and the density. And this, we will call it Maxwellian. With this velocity distribution function, the macroscopic variable like density, flow velocity, and temperature can be calculated from it. So for example, the density, if you want to get the density, you just integrate out the the microscopic velocity. If you want to get if you hit the velocity distribution function with macroscopic velocity and integrate, it will get momentum. And if you divide it with density, you get the flow velocity. Similarly, you can get temperature from the moments. And for kinetic theory, we can consider some boundary condition. One boundary condition is called specular reflection boundary condition. That is, if you have a particle hits a boundary, then it reflects, and with the velocity come in and come out, and the normal vector are in the same plane and with the same angle here and here. And this is called specular reflection. And but this boundary condition is not that physical in the real sense. A better boundary condition is called diffuse reflection boundary condition. That is, when a particle hits a boundary, it will scatter out randomly with two conditions. One is a distribution leaving the boundary is in thermal equilibrium with the temperature of the boundary. And the second condition is there is no net flux across the boundary. That means everybody coming must go out. So that is a diffuse reflection boundary condition. And somehow this is better. This describes the physics better because maybe the surface is very rough compared with the diameter of the molecule. So, and there is another condition called complete condensation boundary condition. This arises naturally for the evaporation and condensation problem. For example, if you have the gas and the boundary are with the same material but in different phase. For example, if you have carbon dioxide as gas and dry ice as a solid, then you will apply this boundary condition. The condition is the distribution going out is a Maxwellian with respect to the vapor pressure of respect to the temperature on the boundary. And there are no conditions for the distribution going into the boundary. That means that the particle hits the boundary just condensed on the boundary.
So that's a strong assumption. That's a specific temperature then.
Yes.
Because normally, so what's between this? That's complete condensation. But what about in between, when there's still collision and vaporization? Okay, maybe your next page.
But I think you can interpolate between these conditions that will make some other models, but these are the most simple one. Simplest one. And first, in this talk, we'll discuss two kinds of singular behavior. One is logarithmic singularity for the macroscopic quantity, and the other is logarithmic singularity for the velocity distribution function on the boundary. So there are two kind of different singular behavior. So the first behavior is that if we denote the distance from the boundary as x, the macroscopic quantity may varies like x log x near the planar boundary. And this phenomena was for for this model, this is a simplified model. This phenomenon was known in 60s and 70s by Sonnen and Onishi. And the computation result for the Boltzmann equation support this. And I'm sorry, I just get this picture from a journal, but the quality is not very good. So this is from Owada, Sonnen, and Aoki's computation result. They deal with a linearized Boltzmann equation on the thermal transpiration problem. And here is the middle of the two plates, and here is the boundary. The phenomena is like near the boundary, the flow velocity has a very little kink. And for another microscopic quantity, this should be the heat flux. Heat flux, it has a kink too.
Can you now explain for us uninitiated the precise meaning of the word transpiration?
Okay, transpiration. Okay. In Chinese, it is translated to 热溢流. And
could you write Chinese capital?
What?
Could you write the Chinese capital?
Okay.
Then probably I can understand.
Well, I also don't understand what the E is. Transpiration.
And in fact, this phenomena is like when you have a boundary, and on the boundary there is a temperature gradient. That temperature gradient would induce a flow, and that flow is not convection. So it maybe it's better to explain a little bit like there was a experiment done by the Tokyo group and Kyoto group. Sorry. So they have a vacant job, big vacant job, and a plate vertically, put it vertically, and they heat downstairs, heat here. So there is a temperature gradient in this direction, and they put a small fan here. So they measure what is the direction of the flow. So the result is when the pressure is high, then because if you heat here, then the gas become heated and become expanding and becomes lighter. So it flow upward. So then when pressure is high, is big, then the flow is in this direction. Then they gradually they use a vacuum pump to pump out the gases. You get the gas inside. And then eventually, at some point, the flow stops. And if you make the pressure even lower, at some point the flow become, I should say low pressure, high pressure. So sorry. When the pressure is low, then the flow becomes downwards, and that is the flow induced by the boundary. So so on this you can see that there is a flow, and more this flow can exist without pressure gradient.
I don't understand. the subscript T means this is this equilibrium or non-equilibrium? When you say there's a heat source, I don't understand the whole picture.
The picture of this.
This UT, the velocity profile, seems to be fixed for a temperature T.
I think it's a stationary solution.
Stationary solution, but
But
then
on the
the
boundary
example you
there is a,
gave, and also you said there's a temperature gradient.
yes, there is
on
a
the
temperature
surface.
gradient.
It's not obvious from the discussion before. In this case, yes, you have a temperature gradient. But if it's steady state, wouldn't it just thermalize? So then, even if it's thermalized, then I don't understand. If it's thermalized and you still have flow?
Yeah, yes. Okay, so maybe we will return to this problem. So here we discuss this kind of small kink near the boundary. And the second kind of singularity is in velocity distribution function. And maybe it's better to see the numerical result from Takada and Funagane. And they compute the velocity distribution function near the on the boundary. And on the boundary there are two things. One is there is a jump in velocity distribution function. That is the distribution coming into the gas is 0, and coming into the boundary is something non-zero. So it has a jump. But more interestingly, on this part, it behaves like C1 log C1. So it has the same kind of singularity. Yeah.
Excuse me, the C1 is on the boundary, right?
Yes, this is the distribution function on the boundary.
The whole thing is the distribution function.
Yes, the whole thing is the distribution on the boundary.
And the C is the position?
This is, okay, so zeta, here we use
zeta,
but zeta is a velocity, the microscopic velocity.
Of the heat flow?
Of the, so we in kinetic theory, we discuss the distribution function of the velocity distribution function. So in different velocity, there are the density of, this means the density of the particle in that velocity. So this is a velocity distribution function. So
Less than 0, you mean zeta smaller than 0 means
the particles will
move.
Particles that move toward the gas region, and for C1 is greater than 0 is a particle move towards the boundary. Okay. So maybe. Okay. So now I would like to explain it. The thermal transpiration is a flow induced by the temperature gradient of the boundary. It can exist without pressure gradient, and it cannot be explained by fluid dynamics. And I think the first explanation in physics is by Maxwell in the paper he published in 1879. And in fact, this is the last paper he had ever published because he died this year. And the key point is he introduced the diffuse refraction boundary condition. So maybe I'll make a cartoon version of his explanation. So So his explanation is, suppose there is no boundary condition, not any boundary condition, then it is possible to have a gas with a temperature gradient this direction, and it is stationary. That is, you have higher temperature here, but lower density. But here you have lower temperature but higher density. But in total, the pressure, the flow is steady. But the problem is, once you have this stationary condition, then if you introduce a boundary with the same temperature gradient, but it is diffuse reflection boundary condition, then it will overwhelm this stationary state. That is because if you put a boundary here with the same temperature as the gas, then here we must emphasize that the gas is very dilute, so it can travel almost without colliding other particles. So it will eventually collide the boundary. So here, if a particle from the cold region, it will have smaller momentum, but the particle from the hot region with bigger momentum. But after collision, it will scatter out randomly. That means that its horizontal momentum totally disappear. So there is a net momentum lost in this direction. So if you calculate the sum of the momentum change, and that is the rate of the momentum change, and that is the total force, then you'll find the total force is in this direction. So that is a cartoon version of Maxwell's explanation on this problem. So, are there any questions? So
you're saying you're introducing a surface
yes.
into this originally stationary situation
Yes.
with temperature gradient.
Yes. Then it's no longer stationary because the air will experience a force in this direction.
What is the physical situation? Because these are not two I'm saying that with the original stationary situation versus a similar situation but with a boundary, the result is different.
Yes. And that is because when it collides with the boundary, it's lost all its horizontal momentum. And the imbalance between those from the hot region and from the cold region, there is a net force. If you calculate the net momentum change, you'll find the air will experience a force on this direction, in this direction.
You're assuming that the other side has no boundary.
I assume the other side there is no boundary.
So what is the full flow then? Where does the flow go?
Flow goes towards the hot region.
So along the surface.
It was induced from the boundary.
But you said there's a force going backwards. So where is the motion? What is moving?
It will move this direction. If this is hot and this is cold, then the temperature gradient is his direction and the flow is in this direction too.
But didn't you just argue saying that the force is towards the low direction, low temperature direction?
Let me think. So, okay. So that is, I should